How's everyone doing? I'm Dr. A.J. Kumar, PhD. We're reading Artin 2.9. This is on modular arithmetic, and of course, first thing we're doing, we're going to go through and highlight terms. Alright, congruent modulo n. Let's do that. Alright. Congruence classes, and I always miss some terms on the first pass, and that's fine. Our goal here is just to get, if I miss a couple terms, it's fine. It's just so that I get the words in my head, and then if there's one that I don't know, then I'm going to look out for it later. And just to kind of get an outline in my head of what the various things we're going to be talking about are, I usually know what the terms are beforehand, because I'm not completely new to this subject. Alright, just looking. This is a real short section, and so I'm, okay, so I know what sum and product is. I think these are not terms. They're there. That's for emphasis, not for marking it as a term. Okay. All right. So this is real short. Let's go with blue and highlight prior references. I don't think there's any prior references. I mean, modular arithmetic. That's basically one of the branches of math, which is called number theory, or arithmetic if you're not pretentious. We're just gonna go. I don't see any prior references actually. 295, but that's just like the previous page. Maybe I should highlight prior references to the previous page in glowy green, because that's a glowy move. It's overusing the numbering function. See, we need to go back to mathematicians having to write everything with typewriters, because the numbering is because then the numbering algorithm is really expensive. If you have LaTeX do it, it's kind of cheating, because then you don't have. Let me set up the highlighter properly for the next time. So big, and we're probably going to want pink. Or green for glowy, but we can go. Oh, and then for the highlighter, we want to turn on the ruler, and then let's go back, and here we go. All right. This section contains a brief discussion of one of the most important concepts in number theory, congruence of interest. That's like the central concept of number theory. If you have not run across this concept before, you will want to read more about it. See, for instance, Stark. We work with a fixed positive integer n, fixed. And so it's the same integer n throughout the section, I think. So we can just replace n in our head with 12. We can just pretend that. And maybe what I'll do is run along with some examples. Okay, just using 12. Okay, so two integers a and b are said to be congruent modulo n if n divides b minus a. So two numbers are different if their difference is a multiple of 12. Or two numbers are equal mod 12 if their difference is a multiple of 12. Or if b is a plus a multiple of 12 for b plus, okay, yeah, 2 is equal to 17 modulo 5 because their difference is 15, which is a multiple of 5. It is easy to check their congruence as an equivalence relation, so we may consider the equivalent. So let's just run through that really quick. It's reflexive, so every number differs from itself by a multiple of 12. Sure. If a and b differ by a multiple of 12, and b and c differ by a multiple of 12, then a and c differ by a multiple of 12, sure, so it's symmetric. And if a and b differ by a multiple of 12, then b and a differ by a multiple of 12. So that's good. Okay, so there are equivalence classes called congruence classes that it defines. We use a bar notation. This is glowy notation. And then you don't even stick with the bar notation because it's fucking stupid. So you never stick with it. That you can tell that some notation is fucking stupid when you don't stick with it. So This bar notation, you use this when you're explaining things to students, and then you stop using it because it's annoying. So this congruence class, we use bar notation and denote the congruence class of an integer a, mod n, by the symbol a bar. This congruence class is a set of integers. A bar is, right, a, the translates of a, but the orbits of a under z mod n. Maybe that's a better way to think about it. Or a, when acted upon by n z. And maybe I should make it bigger so you can see. If a and b are integers, the equation a bar equals b bar means that a is congruent to b mod n, or that n divides b minus a. The congruence class 0 bar is the subgroup. 0 bar equals Zn is the class right, the things that are congruent to 0 mod 12 are also the things that are congruent to 12, so the multiples of 12. Okay, yes. The other congruence classes are the cosets of the subgroup. Please note that Zn is not a right coset. Yes, it is, but it is a subgroup of Z plus. The notation for, oh, here's some wonderful, it is a coset, but he's just, it's a coset, okay, yeah. So, let me highlight this in, let me highlight this in glowy green because this is an important glowy point, which is the glowy notation. The notation, hey, what happened to my ruler? The notation for a coset of the subgroup H, oh, oops. Where, please note that Zn is not a right coset. This is a subgroup of Z plus. So it is a right coset, but with respect to multiplication. Okay, but then it's a coset with respect to multiplication. Okay, yeah, I see what he means. It's not a coset with respect to the. Okay, it's not a subgroup of Z plus, hiding really important stuff in little caves of the notation. It's not a subgroup, or it's not a coset with respect to Z plus. It is a multiplicative coset. So yeah, anyway, notation, but using yeah, right, when we use additive notation, it's A plus H, right, okay. To simplify notation, we denote the subgroup Zn by H. Then the cosets of H, or the congruence classes, are the sets A plus H, which is A plus Kn for K and Z. So the infinite set, which is the multiples of 12s, and then the integers 0 through 11, are the representative elements for our 12 congruence classes if we're analogizing this with Glock arithmetic. There are n congruence classes mod n. Okay, that's just what we just said. There are n congruence classes mod n, mod 12, namely the congruence class of 0, the congruence class of 1, up through the congruence class of 11. The index z to 12z of the subgroup 12z in Z is 12. Right, because there are 12 orbits of 12z in Z. Let A and B be congruence classes represented by integers A and B. Their sum is defined to be the congruence class of A plus B. Let A and B be congruence classes represented by integers A and B. A and B, A bar and B bar, Okay, see, right away we lose the, okay, he's setting up to forget about the bar notation. The sum of the congruence classes is the congruence class of the sum is the sum of the congruence class. So this is the sum of, so these are two different pluses here. This is plus when operating on, so congruence class plus if we were giving this a function name, and then this is int plus. And then this is congruence class times, and this is int times. Right. Right, so, and this works for any A and B, and the point is so whenever you define some, let's highlight this in glowy green because this is some glowy notation, for fuck's sake. Glowy green, here we go. This is some glowy notation because the same congruence can be represented by many different integers. So any integer a prime congruent to a mod n represents the same class as a does. So it had better be true that if a prime is equal to a and b prime is equal to b, then a prime plus b prime is a plus b, and a prime b prime is equal to ab. Yeah, okay. Yes, so, yeah, so it had better, yeah, okay. Right, so that's the lemma. If a prime is equal to a and b prime is equal to b mod n, mod 12, then a plus b prime is equal to a plus b, and a prime b prime is equal to ab modulo n. Assume that a prime, okay, so that a prime is a plus rn and b prime is b plus sn for some integers n and s, then a prime plus b prime, yeah, right, okay. Is, right, yes, okay. This logic is very straightforward. Okay. The associative, commutative, and distributed laws hold for addition and multiplication of congruence. Sure. Okay. Yes. Huh. Okay. I'm not gonna. That seems fine. This is some glowy nonsense. It makes sense. Right, so as soon as you have this, definition that makes sense, then all of the other properties automatically carry over. Because if you have a plus b is equal to b plus a, then, okay, so yeah, so you convert things into everything being defined. So this is the congruence class of a single integer. Then you can manipulate that single integer and then convert it back out to congruence classes by sort of applying your definition in reverse. Okay, by doing your rewriting in reverse. Okay. A set of congruence classes mod n may be denoted by any one of the symbols z, zn, z mod nz, or z mod n. This, I've never seen this one before. In addition, can be made explicit by working with integers and taking remainder. This is what the formula is, 295. Yeah, okay. They tell us that the map that sends an integer is to its congruence class is compatible with addition and multiplication. Therefore, computations that can be made in the integers and then carried over to z mod nz at the end, z mod 12 at the end. However, computations are simpler if the numbers are kept small. This can be done by computing the remainder after some part of a computation has been made. So, thus, if n is equal to 29, so we're saying 12 is equal to 29, so that z mod zn is 1 through 28, then 35 times 17 plus 7 can be computed as, so 35 mod 28, that's going to be 7 Okay, times 17 plus 7 would be, 35 times 24. Okay, so that would be 7 times... Oh, no, 6. I'm sorry. Yeah, 6 times minus 5, which is minus 30, which is minus 1. Okay. Right, okay. See, this is what I was saying. In the long run, the bar... Right, this is how you know it's stupid notation when you don't stick with it. In the long run, the bars over the numbers become a nuisance. They are often left off when omitting bars. One just has to remember this rule to say A is equal to the right. Okay. Congruence is modulo a prime integer have special properties, which we discussed at the beginning of the next chapter. Alright, this was a nice short video. I just wanted to test really my new recording setup on a video that was pretty short. So I will see you later. Thank you for watching. Bye.